Let's get started with some calculus. So, let me actually make sure, yeah, the microphone's on. Okay, so, the very first thing we should note is that we've now got a lot of integration techniques. We seem to be almost inundated with information. So the question is, when should we use each of the integration techniques that we know, and how should we use them? All right, everyone. So the question is, when should we use the integration techniques that we know, and how should we use them, okay? So let's start with the power rule. So our power rule for integration is going to look something like this. We're going to have the integral of some function in the form x to the n dx. That's going to be equal to x to the n plus 1 divided by n plus 1. Sure, plus c. And this one is going to end up reversing. It looks a lot like our derivative power rule, right? So this one reverses our power rule for derivatives. So let's take a look at substitution now. So a substitution, we're going to be looking for integrals that are of the form of f of g times g, f prime of g times g prime. After we integrate, that's just going to give us f of g. Notice if we were to take the derivative and go the other way, what does that look like? If we took the derivative of f of g, that looks like our chain rule, right? So if we took that derivative sign, made it an integral sign on the other side, literally we are just reversing our chain rule. And we'll take a look at integration by parts. That's the newest one. When we do integration by parts, we're not actually solving our integral. We're just converting it into another integral that should be a little bit easier to solve. So we say the integral of u dv is equal to u times v minus the integral of v du. If we were to rearrange this by putting the v integral on the left-hand side, take away the integral signs, make it derivative signs, that looks like our product rule, doesn't it? So this one's going to end up reversing our product rule. I don't think maybe there's one for reversing the quotient rule, but I think that one's just similar to our integration by parts here. So we've got our three main integration techniques. Let's see if we can put these to work. So my first question for you, I'm going to say there are 4 integrals here below. One of them can be solved just with basic integration, just like that. One of them can be solved with a substitution. One of them can be solved by parts, and one of them cannot be solved. So my question for you is, which one's which? Take 30 seconds with a neighbor, and we'll take a look afterwards, okay? Which one is which? All right, let's take a look. So, which one is just a basic integral? Which one can be solved like that? A, that was just from our formula sheet, right? Okay, which one can be solved with a substitution? Oh, that one wasn't as quick. C, D, B. Okay, shout it out all at once. D. All right, let's see. So, the basic integration, this one's A. Let's take a look. So if we were going to try a substitution, I heard a fair bit of C. Someone who said C, what would we substitute here for this one? Let's see. Maybe let's look back to some of our techniques here. So a substitution, we typically want to have some chain rule here. If we were going to look at these functions in terms of perhaps derivatives, or which derivative would give us this, right? If we're saying C is the chain rule, I don't know if it would be. C looks like a bit more of a problem. We'll get back to C in a bit. Some other people said D. Maybe we'll try and do a substitution with D, okay? So if we wanted to solve D with a substitution, we could say maybe we'll let U be the inside function. U is 2x. Then we have du is equal to 2 dx. So dx is equal to 1/2 du. Whoa, look, we have dx right here. So we have a substitution that we're able to make. So this will be the integral of e to the u times 1/2 du. And we can solve this one. We can solve this one right away. This one will just be 1/2 e to the u plus c. So I think this one, I think D is the one that should be the one with the substitution. So we have two more. We've got one which can be solved with integration by parts, and one that we can be solved with one that cannot be solved. Which one of those is which? Which one's the integration by parts? Shout it out. C. So what we're looking for the integration by parts is we're looking for a product of two functions. We're looking for our u dv. Here we have a product of two functions. It's x and e to the x dx. So we'll set u equal to x. We'll set dv equal to e to the x dx. Then our integral will turn into uv. So du is equal to dx. That's just from differentiating. And if we integrate dv, that'll say v is equal to e to the x. So then our whole integral will be, hold on, I'm actually just going to call this I. I is going to turn into uv, which is x e to the x minus the integral of v du. So e to the x dx. And that one's also a little bit easier to solve. So we should be able to do that one and proceed to the final answer. I'm not going to do that here. It'll just be x e to the x minus e to the x. That leaves just one option left. So B, whenever we have a function where it's e to the something squared, and it's nothing else, usually we can't integrate that. So these are kind of classic problems where they can't be solved with elementary, this one cannot be solved. Can't be solved with elementary functions. If you go further into courses in like statistics or anything, anyone have any interest in that? You might end up seeing more stuff on probability distributions and using e to the negative x squared. It's lots of fun stuff. And I think engineering has to. I think everyone has to take a stats course, which is, I don't know. I think it's really important at some point, perhaps, but I'm not sure. Anyways, so let's get into some problems. So we'll do a u sub here. So the question asks us to calculate the integral from 0 to 1 of x e to the power of 4x squared plus 3. So we'll give this one a try. So usually when we have a u substitution question, we're going to want to set our u to be equal to the inside function. So we'll say this inside function here, we'll say u is equal to 4x squared plus 3. Then if we take the derivative, our du will be equal to 8x dx. This is great. We see a scalar multiple of something that's already there. So x dx, that's going to be equal to du over 8. So we'll now sub in our integral. So this will be the integral, call this I. I will be the integral from of du over 8 times e to the u. Okay, I didn't write my bounds yet. So why didn't I write my bounds? Why didn't I write my bounds? We have to remember that when we did this first integral here, from 0 to 1, this is really saying x is equal to 0 and x is equal to 1. But now that we've wrote our integral in terms of u, we're going to need to try and find what u is going between. So when x is 0, we want to calculate what u will be. So u of 0, that'll give us 4 times 0 plus 3, which is 3. And when x is equal to 1, that'll be 4 times 1 plus 3, which is 7. Is that okay with everyone? So we'll sub in these new bounds down here. So we'll integrate from 3 to 7. when we anti-differentiate, this will give us e to the u times 1 over 8. By our fundamental theorem, we'll evaluate it at u is equal to 3 and u is equal to 7. So we'll get 1/8 e to the 7 minus 1/8 e to the 3. All right. Is everyone okay with that example? Any questions about that one? All right, let's press on. So this one might look a little bit familiar. So the question asks us to calculate the integral from 0 to 1/2 from 0 to 1/2 of arc sine of x divided by root of 1 minus x squared dx. Hopefully this isn't bringing up too many bad memories. Let's try and solve it. Let's try and solve it. So I was told by one of the profs that this one was a little bit tricky. This one didn't do too well. So we'll try it here. So we see the derivative of arc sine of x. Also, remember, use your formula sheet. You have a formula sheet, use it. Because the derivative of arc sine of x was on the formula sheet. So the derivative of our arc sine of x here, that is actually 1 divided by the root of 1 minus x squared. So what I'm going to do is I'm going to set u to be equal to the inside. We'll say u, I'll use a different color from the last question. U is equal to arc sine of x. Then our du is equal to 1 over the root of 1 minus x squared dx. So we'll sub in all of that into here. So this right here, everything I circle, that's going to be our du. And the arc sine is going to turn into u, so we'll have the integral of u du. Okay, that looks a lot simpler. So we just have to remember to change our bounds. So when x is equal to 0, we're going to find u of 0. That's going to be arc sine of 0. Since it passes through the origin, that's just going to be 0. And when x is equal to 1/2, we'll have u of 1/2 is equal to the arc sine of 1/2. Arc sine of 1/2, that's pi over 6, right? I think so. That'd be pi over 6. So we'll integrate from 0 up to pi over 6. That'll give us 1/2 u squared from 0 to pi over 6. So that'll give us 1/2 times pi over 6 squared minus 1/2 times 0 is just 0, so minus 0. And that should give us our final answer. So maybe we're not happy with that one, but do we get what went on with this question? Or do we have any questions with that? Let's, oh, question, yeah. Oh no, just stretching? Just stretching. I got you. So I know it might be a little bit painful to look back at some of these questions, but it's okay. Now we know for the final, right? So let's keep pressing on here. Let's keep pressing on. We're going to talk about integration by parts for a bit, because I don't know about you guys. When I first saw it, I thought it was a huge mess. Why are we doing all this? How are we doing all of this? So we'll try and piece together some methods or kind of rules to follow that might simplify the procedure a little bit. So we're going to first look at a method. You could think of it as the I'm late method or the Liotte method. They have slightly different orders, but it should be roughly the same. So what this stands for, what Liotte stands for is logs, inverse trig functions. A stands for algebraic, so like anything polynomial. T stands for trig, and E stands for exponential. And what Liotte does is it gives you kind of an order for choosing which function should be your u function. So this helps you choose u. Helps you choose u. So let's take a look at the Liotte method for this question. So if I wanted to use Liotte here, we'll check, do we have any logs? Yeah, we do. We have the ln of x. So let's choose u to be ln of x. So if u is ln of x, our dv is just going to be everything that's left over. So our dv will equal x squared dx. So we'll take the derivative of u, which is du. So du is equal to 1 over x dx. Our dv is going to be, if we integrate it, we'll get 1 over 3x cubed. Don't worry about the plus c yet. So then what'll happen is our integral I, that'll turn into, we'll have uv, so ln x times 1/3 x cubed, minus the integral of v du. So 1/3 x cubed times 1 over x dx. Oh, that's handy. Because this x cubed and the 1 over x will cancel, and it'll turn into something that's a little bit easier to integrate. So this integral, I'm just going to reorder this a little bit. 1 over 3x cubed ln x minus the integral of 1/3 x squared dx. That'll turn into 1/3 x cubed ln x minus, we'll use our inverse power rule, so we'll add 1 to the power, so it'll be x cubed, 1 divided by 9. Don't forget the plus c, and then everyone will be happy. Cool. So do we have any questions with that one? Now, I did talk about a second method, or I'll let you finish copying that down. I'm just going to zoom out a bit. I'd also mentioned the DI method as well. So I encountered in the last tutorial that this was a bad example to try the DI method on. So I'm just going to bring up one more example really quick. You may or may not have seen this in class, but in case you haven't, if you want to do an integration by parts, that might take a long time. So for example, we'll do x cubed e to the x dx. Here's a little shortcut. So here's what our shortcut's going to be. We're going to make a little table, the little DI table. This is what it's going to look like. We're going to have a D here, an I here, and I'm going to have alternating plus and minus signs on the left. And all we're going to do is we're going to put our choice for D. Our algebraic will come first. So we'll put x cubed here for D. We'll put e to the x in the integration column. And all we're going to do is we're going to take the derivative until we hit 0. 3x squared, 6x, 6, 0. We'll also take the integral until we get to that same point. Lucky for us, that's e to the x. And then all we're going to do is we're going to multiply downwards. So we're going to multiply like this. And we're going to take the sign from this. So it's going to be a little bit weird, but we'll multiply down like that, and such. So our integral for the whole thing, it'll turn into x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x. And then you're done. That's handy, right? That's quicker than choosing u, du, integrating each time. So if you have a function that looks like this, I'd encourage you to give it a try. I like it a lot. Now, as soon as I told you about that, though, we're not going to use the DI method on this example. Because this doesn't even look like an integration by parts problem, does it? Well, let's think, okay? We've done lots and lots of stuff with logs. We took the derivative with logs. We know the log is the integral of other stuff. Right? We know the log is the integral of 1 over x. So my question is, what is the integral of a log? Now that's a tough one, isn't it? I don't think we've seen that before. But let's see if we can choose something clever to help us. So we don't know how to do this one with a u sub. We chose x to be u. It wouldn't really get us anywhere. Oh yeah. I'm sorry? How would you approach this one?
Is that where you said g prime of x, like g of x is 1, that way g prime of x is, sorry, g of x is x, so g prime of x is 1.
Aha! You mean for a u sub, or do you mean for an integration by parts? I'm not sure. Do you mean for g, you mean like our v, our u and our v, right? Yeah. Oh, my bad. Different conventions and stuff. But yeah, that's absolutely right. So what we can do here is we can say, all right, let's set u to be equal to ln of x. We'll follow our Liotte rule. And we'll set v equal to, dv equal to 1 dx. 1 would fall under our algebraic. Okay, that looks a bit strange. It looks like we've just overcomplicated this integral. But let's see, we'll give it a try. So if we take du, that'll be 1 over x dx. Our v would be equal to just x. And let's try and integrate. So our integral I, that'll be equal to uv, which is x ln x, minus the integral of v du, so x times 1 over x dx. Oh my god, that's handy. X times 1 over x cancels to 1. So we're left with x ln x minus the integral of dx. Whenever you integrate d something, that just gives you that something. So we'll be left with x ln x minus x. And remember to put our plus c when the final integral goes away. Everyone happy with that one? All right. We'll move swiftly along. We're going to get into some stuff that is a little bit trickier. How do you guys feel about the volumes of rotation stuff? Big thumbs down? I'm going to be honest, I think volumes of rotation is the most difficult part of this course. But maybe we can try and take a look at it and see if we can together make it seem a little bit less scary. So let's give it a try. So we're going to talk about Isabel. Isabel, are you in here? It's okay. All right, that's fine. So Isabel loves figure skating with her synchro team. They end their routine with a spin, centered, and rotated around the x-axis, finished by the region in the first quadrant, bounded by the curve y is equal to root x secant of x, and x is equal to pi over 4. Find the volume made by the spin. That sounds like a lot of stuff, a lot of words. But let's piece it together. So they start by saying that we're in the first quadrant. That means that x is 0 and x is bigger than 0 and y is bigger than 0. So we'll draw our first quadrant bounds here. This is our quadrant 1. It tells us that the curve is given by root x secant of x. I don't know what that looks like. I'm guessing you guys also don't know what that looks like, but that's okay. We're just going to kind of draw some filler here to see if that, maybe it'll look something like this. We're being really hand-wavy here, but the thing is we don't actually need to know exactly what it looks like. But we'll assume it looks something like that. Actually, I'm going to redraw it like this. It also tells us we're bounded by x is equal to 4, or x is equal to pi over 4. So we'll be bounded on the right. So our region is everything in between. Our region is everything in the middle. So let's talk about the next part. It says we're rotating around the x-axis. So let's draw the rotation here. When we take a look at what's actually happening, right now we've got our two axes that go this way and this way, right? I want you to imagine a third axis coming straight towards you. So that third axis will be right in this third dimension here towards you. What's going to happen is our graph is actually going to rotate around that axis 360 degrees around. So it's literally going to go rotate towards you with the same radius. It's going to form a circle of the radius of the height of our function. Isn't that fun? So what's going to end up happening is after the rotation happens, here I'll draw our original arm of the function. But we're also going to end up with an arm of the function down here, and also everything in between. If we were to draw it in, if we were to draw it in 3D with 3D planes like this, it would look something like, how do we even want to do this? It would look something like this. So something like that, but I think that's a little bit tricky to visualize. So what we're going to do is we're going to take a look at, we're going to try and compress it down to some 2D stuff, because it's a little bit easier to work with 2D. So we're going to take a look at two views of one specific disk. We're going to look at a disk from this volume here. This is our disk in green. So if we look at our disk from the front, it'll look like this. And if we look at our disk, oh, sorry, this is from the side. If we look at our disk from the side, it looks like this. And if we look at the disk from the front, so if we look at it from the front going this way, our disk will just be a circle. Okay, we'll pause there for a sec. Is everyone okay with that? So we're looking at our disk from the side. It'll give us this right here. And if we look at our disk from the front, it's like that. Like our circle. So my question is, let's simplify our problem. Let's say we just wanted to calculate the volume of this disk, this cylinder. How do we calculate the volume of a cylinder? Volume of a cylinder. Got to think back a couple years for that one. We've got to find the area of the circle and multiply the area of the circle by the height of the cylinder. That sounds familiar, right? So we'll multiply our area of the circle times the height of our cylinder. Here, our height, since the cylinder is rotated on its side, our height is really our width. And its width right here, that'll be dx. Let's remember the area of our circle. We'll take the radius here. And we want to find area is equal to pi r squared. Our radius will actually just be the function itself. So it'll be pi times the square of root x secant of x squared. So that'll be pi x times secant squared of x. Okay, and now if we want to find our volume of that one disk here, that'll be pi x secant squared of x times our height or our width, which is dx. Okay, is everyone okay so far with how I set up that volume of the cylinder? So now my question is, now that we know the volume of the cylinder, how are we going to find the volume of the entire region, the volume of the entire shape? Well, we know how to use sums, but we want to do a continuous sum here, so we're going to use our integral. All we're going to do is we're going to integrate it. So we'll integrate that pi x secant squared of x dx from 0 up to pi over 4. Those are our bounds for x. Remember, x is equal to 0 is here, and x is equal to pi over 4 right here. So after we perform this integration, let's see, we've got a product of two functions, x times secant squared of x. So maybe let's use integration by parts. So I'm going to, here, let's put this integral over here. So we have the integral, actually, just going to copy this over. What? Jumps around a bit. All right, so we've got this integral here. I'm going to set u to be equal to x. According to our Liotte, we'll set dv equal to secant squared of x dx. So if we want to take the derivative of u to get du is equal to dx, and we'll integrate v. Remember, the integral of tan squared x is just secant squared x is just tan x. So remember, this integral will turn into uv, so x tan x, minus the integral of v du. So the integral of v, which is tan x, times du, which is dx. All right, this looks a little bit nicer. So if we were to evaluate this on the left here, that would give us pi over 4 times tan of pi over 4 minus 0, because, that was silly. Minus 0, because when x is 0, that whole thing will go to 0. So now we're also going to need to integrate the thing on the right. So I'm going to just say that's the integral of 0 to pi over 4 of sine x over cos x dx. So we might want to make a u sub for this one. So my question is, what would we choose here to be the u? What do we choose, yeah?
Cos x.
Cos x, why not sine x? I was thinking we should choose sine x.
We won't be able to form
Exactly. So if we had chosen sine x, we wouldn't have been able to find a du anywhere in here because our cos x is in the denominator. That's a problem. But if we chose our u equal to cos x, then we see our negative sine x up there, and we can make a substitution for it. So we'll choose u is equal to cos x dx, cos x, du is equal to negative sine x dx. We have a negative sine x dx right there. So after we integrate, here I'm just going to write this out, pi over 4 times, and tan of pi over 4, what's that? That's 1. Minus, we'll have the integral of, I'm going to turn the minus into a plus, just cancel with the negative sine x here, and we'll get du over u from 0. Oh, and we have to change the bounds. So when x is equal to 0 here, u of 0 is equal to cos of 0, which is 1. When x is equal to pi over 4, we'll have u of pi over 4. U of pi over 4 will be equal to cos of pi over 4. That should be root 2 over 2. So after we sub this in, we'll have from from 1 up to root 2 over 2. This will give us pi over 4 plus ln of the absolute value of u, evaluated from 1 to root 2 over 2. We'll get pi over 4 plus the ln of root 2 over 2 minus, and ln of 1 is just 0. So this is going to be our final answer. All right. Is everyone happy with that one? Oh, question, yeah.
I think there might be a pi you need to multiply.
Oh, did I miss a pi? Did I drop that somewhere? Oh, I dropped that all the way back there. That's a big no-no. That's my bad, guys. So we'll, thank you for catching that. I'm going to just multiply that by pi. Multiply by pi. Multiply by pi. Multiply by pi. So our final answer will be that times pi. Is that better? Thanks for catching that. All right. Everyone okay with that one now? Awesome. All right. I still see some people copying. Do you want me to leave it up there for a couple more seconds? Maybe I can see if I can pan to the other question at the same time. Oh, it might be a little bit of a stretch. I'll post these afterwards. Okay. We'll head over to average value. So Kristen and Foz love typing. They're playing a type racing game. And if seeing how fast they can type combined. Their combined typing speed over the 2-minute game is given by the function of x is equal to e to the arctan of root x divided by root x times the root of 1 minus x. So my question is, okay, let's say f is in minutes as well. F is in minutes. So how many words did they type between 30 seconds, so that's 1/2, and 45 seconds? And at what points were they typing at exactly their average speed? So let's see, we'll take a look at this one. So first, how many words do they type between 30 seconds and 45 seconds? For this one, we should be able to set up an integral. So we're going to be taking the integral from 1/2 to 3 over 4 of f of x dx. So we'll say e to the arc sine of root x divided by root x to the root 1 minus x dx. All right, so how are we going to solve this integral here? So which integration technique do you think we should use? Think about this one. It looks like we've got a function on the inside. We've got multiple inside functions here. We see a derivative here that's common to each other. Maybe we should try a substitution for this one. So we'll give it a try. What could we use? What could we use for our u? Let's see. Yeah. Square root of x. That's a good choice. Let's try it. We'll see what happens. So let's say we chose u is equal to the square root of x. Then du is equal to 1 over 2 root x dx. So we see that partially here. The thing is, it's difficult to find a way to substitute that x in the denominator. You see that root 1 minus x? It's a little bit hard to take care of that one. So I think you've got a good idea. I think we're on the right track. But maybe there's slightly different functions to DRU. Yeah. Yeah. Let's try arcsine of root x and see what happens. So if we chose u equal to the arcsine of root x, then our du will be equal to, now remember, we'll get 1 divided by the square root of 1 minus root x squared. We'll need to multiply by our chain rule, so we'll take the derivative of root x. This should give us 1 divided by 2 root x times the root of 1 minus x. That looks a little bit more promising. So we'll plug that right in here. We'll perform our substitution, and that should give us the integral from of e to the u of, now we have the root x and the root 1 minus x, but we haven't taken care of this 2. So if I multiply the 2 to this side, we'll get 2 du. That ends up actually not being over anything. We do need to find our balance for u. So if x is equal to 1/2, then we should have u of 1/2 equal to, that'll be arcsine of 1/2. Arcsine of 1/2 should be pi over 6. And if x is equal to 3/4, u of, oh, sorry, that should be root of 1/2, shouldn't it be? U of 1/2, sorry, I'm skipping too many steps here. That's my mistake. Arcsine of root of 1/2. So arcsine of root 2 over 2, that should be pi over 4. Then u of 3/4 is equal to the arcsine of root of 3/4. That's root 3 over 2, so that should be pi over 3, right? Should be pi over 3. So we'll be integrating from pi over 4 up to pi over 3. That'll give us 2e to the u, pi over 4, up to pi over 3. So that'll give us 2e to the pi over 3 minus 2e to the pi over 4. How does everyone find that one? Is that okay? So now the second question is, at what points were they typing at exactly their average speed? So let's think back to our mean value theorem here. Remember, our mean value theorem tells us that if we have some differentiable function, we can say that there exists some c on the interval where the instantaneous slope is equal to our average slope. If we were to integrate that, we could basically say there's some point on our function, there's some f of c, where the average value of the function is equal to that function point. So basically what it's saying is, okay, we're going to try and find our f of c where c is equal to our average value. So our average value would be, we would actually have to divide by the interval length, actually. 2e to the pi over 3 minus 2e to the pi over 4 divided by our length of the interval. So the length of the interval here, that would be 3/4 minus 1/2. So then we would have to solve an equation here, which is very, very, very ugly. E to the arcsine of x over root x, root 1 minus x. If you wanted to solve it, this is how you would do it. You would solve that equation. There's no way they'll ask you to solve this kind of equation. I think that's very, very, very messy. You're welcome to try it, and if you get an answer, you can. I would love to hear about it. But I think we're gonna bypass this part for this part of the question. So don't worry too much about this part B for this one. All right, we're gonna move swiftly along. We've got 2 more examples here. We're gonna start by doing a trig integral. So what I'm actually going to tell you is we're going to start with a simple rule that we can use whenever we have copies of sine and cos. So whenever we're integrating powers of sine, so sine x to the nth power and cos x to the mth power, we can integrate it easily as long as one of m and n are odd. So if n is odd for this one, make u equal to cosine of x, and then we'll turn all but one of our sine x's into 1 minus cos squared x. And we can do that because if n is odd, then all the rest of the sine x's will be, like if we save one sine x, then all the rest should be an even number. Same thing for m. If m is odd, you do the opposite. And if they're both odd, then it'll actually be either. You could choose either. So let's see if we can use this strategy to help us solve this integral. So we're going to try and integrate sine squared x times cos cubed of x dx. We see that cos cubed of x is odd. So we'll use the opposite technique here. So we'll set u is equal to sine, We'll set u is equal to sine x. Then we have du is equal to cosine of x dx. We'll also manipulate using this equation. So we'll see that u squared is equal to sine squared of x, which is equal to 1 minus cos squared of x. So this is cosine of x is equal to, cos squared of x is equal to 1 minus u squared. So now let's see if we can make a substitution with it. So we'll substitute that into our original integral, and we'll get the integral of u squared. Actually, I'm going to rewrite this one more time. We'll have sine squared x times cos squared x times cos x dx. This cos x dx will turn into a du. This cosine of squared of x, that'll turn into the 1 minus u squared. And this sine squared x will turn into a u squared. So we'll be left with the integral of u squared times 1 minus u squared du. So this one should be a little bit more easy to solve. We can expand this one out. So we'll get the integral of u squared minus u to the 4 du. And we can just solve this one. We'll get 1/3. No room here. We'll solve this with 1/3 u cubed minus 1/5 u to the 5. Don't forget the plus c. All right, so this kind of example is, or I guess this rule here, is just a quick way to simplify integrals of sine powers, cosine powers. You could also extrapolate those to the secant and tan powers. Those go together. And you could also extrapolate to the cotangent and the cosecant. All right, does anyone have any questions about that example? We'll take a quick pause here. Around this point in the last tutorial, people had some questions about the volumes and also some other questions, I guess, going back. Do we have any more questions about anything that we've done today? If not, I have one more question for you guys. Let's see if we remember how to do this stuff from the very beginning. So I have 4 more integrals. One of these can be solved, it's a little bit different. One of them can be solved with a substitution. One of them can be solved with integration by parts. One of them can be solved with either method. And one can't be solved with any technique. So I'll give you another minute. Take a look, have a discussion with a friend, and we'll talk about that in when we regroup. Yeah, you should touch that. That's we'll stop that. Let's stop that back in really quick. Good catch, thank you. It's a little bit sloppy that I didn't have to Did you say that too? Oh no, never mind. What did we say u was? U is sine x. So this is 1/3 sine cubed x minus 1/5 sine. All right. Sorry guys, I'll put this back up here. Let's take a look together, shall we? So which one is the substitution? This one's a bit of a trick. Just shout it out. Which one's the substitution? Need a little bit more time to think about it? Here, oh sorry, I should put, maybe I'll put A, B, C, D here. So which one's the substitution? Lots of C's and A's here. We'll see. Okay, which one's by parts? We should know that one from today. B. Let's see. So this one's by parts only. Okay. So we said A and C for substitutions. Which one can be substitution or by parts? C, you're right. Because here we have a product of two functions and we also see the derivative of the function. So this is oh my gosh. Substitution or by parts. What's A then? A is our substitution. And then by product of elimination, D cannot be solved. Womp womp. That one can't be solved. So it's very interesting because with our derivatives, if we have a function expressed in elementary things, we have products of polynomials, whatever functions we can write down, we can always find what the derivative is. But sometimes, even if the integral exists, we might not be able to write it down. So this 1 over ln x is an example of that. All right, any last questions? All right, so next week will be our last tutorial. It's very sad. You guys are one of my favorite classes to work with. So we'll come back. We'll have a great last tutorial next week. You will be there. Thank you so much, guys. We'll see you next week, okay?